This is going to be your lecture on the topic kinetostatic analysis, force analysis with kinetostatics, and we are going to look at the matrix method. This is section 10 in our notes. I mislabeled there, section 10. In this set of notes, I'm going to give you an introduction to force analysis. Actually, you've already seen force analysis using the method of virtual work. In this case, we're going to cover a kinetostatic method called matrix method, and I'm going to give a little review of dynamics. All right, so let's dive right in. Introduction of force dynamics. In dynamic force analysis, the idea is you create these equations of motion that relate forces and motion to the bodies in the mechanism. These are called the equations of motion. You know, really the governing equations to some degree of everything, and they are written in this form: F equals ma. Of course, this is a Newtonian-based format here, and that's what we're considering. Where F is the sum of external forces acting on the body, mass, that's the mass, and then acceleration is the acceleration of the center of mass about with respect to a inertially fixed frame. So this is our governing equation. I've used bold here to indicate that these guys are vectors. You know, there's two, and then we call this Newton's second law. There's two directions to this problem you could consider. One being the forward dynamics, and then one being the inverse dynamics method. So I'm going to list it this way. It's a little odd how I'm going to draw my arrows, but I guess this is the naming scheme I'm going to use. So if I got F equals ma, if I go from a given state of motion and want to solve forces, I'm going to call that the forward dynamics problem. And if I want to go from a given input force and want to find the resulting motion, and oh, by the way, the internal constraint forces, I'll call that inverse dynamics. The forward dynamics, spell that right. The forward dynamics problem, that's the one we're going to be covering here, and sometimes we call that kinetostatics. You know, some might be a little snobbish and say, well, you're not really solving. They might say, well, are you solving second order differential equations? And we're not going to. We're going to be solving linear equations for the forces. So they'll say, well, you're not doing dynamics. So, you know, maybe to avoid arguments with people that are a little snooty, we call it kinetostatics. This idea is we're keeping the motion fixed instantaneously, solving these force balance equations, coming up with the equations, and then appropriately moving forward. The inverse problem, to be fair, you know, the inverse dynamics problem, some would call this is the classical dynamics problem. And to be fair, it's a much more complicated problem. In this case, well, okay, so in this case, I'm gonna let me say for the forward dynamics, I'm gonna, you know, hold everything still instantaneously, just fraction of time, instantaneously. So it's sort of an instantaneous problem, I guess we could also say instantaneously. And then I'm going to solve and while I do that, then I'm going to solve the force balance using Newton's second law. You know, say, hey, there's acceleration instantaneously. This is the state of acceleration. Let me solve a force balance. On the inverse dynamic side, I don't have to do that, but I do have to, going back, and when I do that, I can get these linear equations that I can solve, linear equations. Okay, back to the inverse dynamics problem. I can, you know, I don't have to do that instantaneous mess, but I do have to solve these problems that are second order differential equations. And if that's not bad enough, I also have a set of constraints to solve. So it's you know, it's not a problem for the faint of heart. It's a nice straightforward problem. And actually, to some degree, you could make the case that you could somewhat get this similar information by solving kinetostatics in a responsive sense, but you're not going to get this governing this equation describing your motion, but you'll practically get the same answers. But anyhow, we are focusing on the kinetostatics problem in this class. And then I want to state one other thing. you had your dynamics class. You've also had, or you're going to be having DMC, where you're going to look at the solution. You're going to look at the inverse dynamic solution. You're going to write the solution to solve for the motion given some input force or no force. So you'll solve a particular solution, a homogeneous solution to that problem, particularly second order problem. And that's great if you have a single particle. We have nice, for a bounded class of problems, we have closed form solutions, pretty narrow. And that's what you looked at the dynamics class and in the DMC. The issue at hand here is that we've got these multi-body, right now planar, but multi-body systems. They're not going to deliver a problem that has any type of closed form solution. So you're really going to be forced to go numerical at some point or another. So, okay. Anyhow, that's the nature of this problem. So we got the forward dynamics and the inverse dynamics problem. And then I've got some motivational points. This is going to add significantly to your mechanism modeling skills, going to give you a lot more information. Getting these forces, particularly getting these forces, is a function of time, kind of being able to look at different motions and different external loads, how that affects the internal force and the driving forces. That's really critical for your design. And then I've an old Dilbert cartoon that I thought might be motivational. As engineers at Tennessee Tech, you're definitely learning the hard stuff. No one's going to question where you're going to get a job. Okay. A few things here. A little review of dynamics. So Newton with 3 laws. The first one I say is conservation of momentum. So body at rest stays at rest. So, if acceleration is 0, then the force equals 0. Second one is force equals rate of change of momentum. So momentum is mv. If I take the rate of change of that, assuming mass is fixed, which is kind of typical, maybe not in rockets or certain things where I'm getting rid of mass, but generally we assume mass is fixed. In that case, mass is constant. So we get mass times the derivative of velocity or acceleration, and that is defined as force. This is why I call this one Newton's second law. And then the third equation is the action-reaction. So I've got a body, let's say no mass. Let's do this. If I have 2 bodies and I'm looking at that intersection here, I pull them apart like so. There's a, let's call this one 2 and 3. There's a force of body 3 acting on 2, and there's the x component and there's the y component. And similarly for this guy, there's a force of 2 acting on 3, x and y. I don't know the direction, so I just assume they're positive. But Newton's third law says that action, reaction, these things are equal. So the force of 2 on 3 has to equal negative 3 on 2. And the force of 2 on 3 in the y has to equal negative 3 on 2y. And that's Newton's third law. Okay, let's see, I say some key points. The key points I should have placed up here. This F is the sum of forces. And then the acceleration is the acceleration of the center of mass. Has to be the center mass. Oh, and these are some of the forces acting on the body, acting on the body. And then mass is mass. I think that's straightforward. Down here, there's a corollary. I call it a corollary. Gosh, Euler wouldn't be happy if I called this a corollary, but sometimes we call this an Euler's equation, so we could add to it the rotational portion. Now, there's a 2D is very somewhat simplistic. In 3D, it gets more complicated because for the same reason that we said we cannot use this complex polar notation to go from 2D to 3D. We have to use a Cartesian, some other, there's a variety of types, but I'd suggested a Cartesian notation. So similarly, Euler's, the extension to rotation is going to get much more complicated between 2D to 3D. So make sure we're only talking about 2D right now. There's other terms that show up, but the corollary would be that the torque is equal to the rate of change of angular momentum. So T equals the ddt. Angular momentum would be an I. Angular velocity omega, which is the I, assuming I is constant, the omega dt. So I alpha. And and there's a couple really key points about this. We want to write this guy. So the torques, which I'm going to say is torque is the sum of moments or the sum of torques about the center of mass, okay, is equal to I alpha about the center of mass. I'm just going to CM. And then the I correspondingly has to be taken with respect to the center of mass. Now, there are a couple special cases. You can take this about a fixed point. There's a special case where you can take the sum of torques about a fixed point and say that's I about the fixed point times alpha. That can be shown. And then you can also say the sum torques about some generic point, I'll call it D, is I about D times alpha about D plus mass R cross mass times the acceleration about of D. Okay, but we're not going to do that one. I for our purposes, let's just take it about the center of mass. Really not much. I don't think that there's really much work lost about that. So I've talked about here, but we're going to some moments here. I'm saying CG, center of gravity, kind of assuming a uniform gravity field means center mass and center of gravity are the same. That's always going to be the case, except if you're in orbit and you've got a large body, large enough that the gravity is somewhat changing. You know, like gravity from Earth is somewhat changing from one end to the other, and you really care about small moments. But on the types of problems we do, that's all we have to work on. Okay. And again, in 3D, it's a different beast. It's fun to talk about, but we're not going to talk about it right now. A few other points to review. There's the idea of a two-force member. If you have a two-force member, which assumes the mass is equal to 0, and there's only two forces, you can then assume that the forces have to be acting in the direction of the body. So, there's nothing to support. No moments. Yeah, moment and is 0. Actually, I said that mass is 0, and then also no moments, no torque or no moments. I'm going to use those interchangeably, moments or torque. No moments acting on it. You can choose a two-force member. A lot of times, if we have a cable, that's an obvious two-force member because it can't carry moments. And then with a cable, we probably want to add the addition. We assume that's in tension only. Okay. So I got 3 methods here actually. Superposition, because these problems are linear, you can consider just one external component at a time and then add them up. Or matrix method, you check everything at once, which is what we're going to do. Or the third method is virtual work, which we've already covered. So let's look at the method of the matrix method, kinetostatics with matrix method. In this method, the equations of dynamic equilibrium are written for free body diagrams, all the lengths. Okay, so I got to create free body diagrams, all the lengths, write my Newton's second law, dynamic equilibrium for each link. They're going to be scalar. I'll write it for the x, y, and the sum of moments. That's going to give me a system of equations that are linear in the forces. I'm then going to write them out this way. So, some coefficient matrix times my vector of unknown forces, and here I'm saying forces and torques equals MA. And then I'm adding the torque term as well and the I alpha. So I guess I've just written the same thing. All right. And then in general, there's going to be a lot of unknowns. So you're going to get a matrix that's it's not going to be 2 by 2. It's going to be large, 9 by 9, 12 by 12. Who knows what it'll be? So, using your computer, calculator, MATLAB, Excel, some other tool to solve. All right. So I've got a step-by-step. You'll need vector labels on the body. You'll need vectors going from each. Okay, this is wrong. It needs to go from the center of mass to the joint. You want to go from the center of mass to the joint. So it says joint to center of mass. So you need vectors going from the center mass of each joint, center mass out to the joint, and also a vector going from the center of mass, to point of force application. I got those backwards. You'll construct free body diagrams of every body, except for ground. You don't know all the forces on ground. You write your equations of equilibrium, express the scalars. And remember, they are the sum of forces in the x equals MAX. Sum of forces in the y equals MAY. And sum of moments and I was using torques above, now I'm saying moments. Remember, it's going to be about the center of mass equals I center mass, and I will call that sometimes G times A. So, oh, alpha. Oh, you know what? Alpha. Okay, and let me say something. So this is the right way to say it. Let me point out something I think I did above. Huh. I wrote this here. I said alpha center of mass. That was a little confusing. It wasn't wrong. Alpha is the same anywhere on the body. I don't know if we've made that clear. So if this is my body, very arbitrary, this is the center of mass. You can think about alpha about the center of mass. That's fine. Or you can think of alpha about here. That's fine. Or you can think about alpha over here of the body. That's fine. They're all the same alpha, all the same alpha. So it doesn't matter. Alpha is the same anywhere on the body. The I is very much a function of where you take the mass moment, I's mass moment of inertia. And it does matter where you get that mass moment of inertia. Might want to do a little review of that. We want the mass moment of inertia here. That I, not the area moment of inertia. So this is the mass moment of inertia. Okay. So we have to write equations for each. We then write our equations in matrix form, and then finally we solve. If we have that big matrix of C times our vector of unknown forces equals MA, to solve, we say that our forces equal the inverse of C times our MA. And I'm making MA and F generic to cover both torques and forces. A few special cases, you might get a case where two bodies come together. That means you're going to need kind of forces between 1 and 2 and forces between 1 and 3. Maybe an easy way is just create a little infinitesimally small split. So you have 1, 2, and 3. We saw the same thing in mobility. If you have gears, that contact, remember that's a higher pair contact, but that means the direction of the force between the gears. It's along the axis of the force. Okay, I guess those are two examples. Okay. I'm going to quickly look at I'm going to kind of outline a few things, two things. Okay. So here's a generic 4-bar, and I've drawn these funky looking links just to show, and I've shown center of masses throwing out there. So let's take a look at this guy. I would want to create vectors going from the center of mass out to each joint or out to each body. This was body 1, 2, 3, 4. So I'm going to use this consistent naming scheme. I'm calling this R21. So that's the vector of the center of mass of 2 to body 1. R22, that's the center of mass this is the vector from the center mass of 2 out to body 2. Up here, notice I've got R32. That's the vector from the center mass of 3 to body. I guess actually, let's call that R body 1, and then this would be R from the center mass of 3 out to body 4. So I might change that. And this would be the R from the center mass of 4 to body 3. And this would be R from the center mass of 4 to body 1. That's kind of a nice way to do it. So I've got those guys. And then let's see what I'm going to have. I'm going to then see, I got on the next page. Okay. I'm now going to construct free body diagrams of all the bodies except ground. So I'll get a FBD of 2. I'll get an FB, that was body 2. I'll get an FBD of 3. And I'll get an FBD of 4. Okay, let's do this. Kind of had this stuff above. So I had some center mass of 2. I'll call that G2. So I had this R21, R22. Okay, these are revolutes, so they're going to have forces acting at each of them in the X and Y. I don't know the directions. I might have a guess, but I'm always going to assume they're positive. That way, whenever I solve them, I know I assume they're positive. So if the sign is positive, I know it's in the positive X. If the sign is negative, I know it's in the negative X. Makes it easy. And I'm going to name them this way. I'm going to say this is the force of body 1 acting on body 2 in the Y. And this is the force of body 1 acting on body 2 in the X. Up here, I've got these XY forces, positive direction. This is the force of body 3 acting on body 2 in the X, and force of 3 acting on body 2 in the Y. See how easy that is? And then let's go up and peak. There was an input torque here, so I'm going to add that to my free body diagram. So there's some T in And then finally, I don't want to forget mass times acceleration, up to mass times mass of 2 times gravity. And that's going in the negative y. All right, now we jump over to body 3. I get a center of mass G3. So I get a vector going from center mass of 3 to body 2, and a center R going from the center of mass of 3 to body 4. I get forces on each of these pin joints. This is going to be the force of 2 on 3 in the y. That was in the y. And this is force of 2 on 3 in the x. And this is the force of 4 on 3 in the y and 4 on 3 in the x. Once again, I get a mass of 3 times gravity. And then we come over here to our third body. Here's my our fourth body, G4. I get these vectors. So this was R from 4 to 3 and R4 to 4. And I would know these vectors, by the way, from the position problem. That's why we did all that work. I get the reactions here, and I don't know the direction, so I just assume they're positive x, y. I'll call this the force of 3 on 4 in the x and force of 3 on 4 in the y. Notice I'm looking at the force acting on the body, and this is force of 1 on 4 in the x here and 1 on 4 in the y. Okay. I got my mass times gravity, mass of 4 times gravity 4. Now, if for fun in this problem, I'd have said, oh, hey, there's this other external force acting on it somehow. Who knows where? Oh, well, look, I said I added a T4. And let's say at the center of mass, I'm also adding a force P of some value, just give it. Well, what do? Well, I just go put them on the free body diagram. So I had the T4, and then if there was a P or something, I would add that in. Okay. So there's my free body diagrams. Now I've got to write the equations. They're going to be sum of forces in the x, sum of forces in the y, sum of moments about the centroid. So this is going to be about G2. Sum of force of the x. Well, I got F1 on 2x plus F3 on 2x. Need to make it legible. Equals, there's no other force in the x, equals massive body 2 times AG2x, the acceleration of the center of mass 2. Now for y, force of 1 on 2y plus F3 on 2y. I've got gravity acting in the negative y, so minus m2g equals the acceleration, m2ag2y. Finally, the moments, okay? So what do I get for moments? Well, a moment is defined as a r vector times an f vector. So I get r21 vector crossed with the f12 vector plus r22 vector crossed with the f32 vector, okay? These are vectors. And I get that T in, and that's all going to equal I about G2 times alpha 2. Now, if you remember the cross product rules, let's tag it over here. General R cross an F, which we might call a moment. What's it look like? Well, it's R. The X component or the YI component is RY FZ minus FZ X RY. I'm kind of reminding you of this. A couple different ways you can do it, but I'm just going to give you the, by definition, the J component is RZFX minus RXFZ. Now, by the way, we don't have an FZ, we don't have forces in the Z direction. I got carried away. RYFZ minus RZFY. I was talking already. Okay. We don't have an R or an F in the Z direction, so they're going to go to 0 kind of nicely. Let's carry on. RZFX minus RXFZ. We don't have those guys. There's nothing in the Z direction. Okay, what about the third component, the K, which is the Z direction? Funny how we have all these different names for the same thing. We get an RXFY minus an RYFX. Voila, we do have a K term. I mean, I do have a direction in the moment in the K. See, so it's coming out of the board, and it's RXFY minus RYFX. So I come back over here, and I got an R21X F12y, that's an x, not a cross, minus R21y F12x. That's my first term. Plus this guy, R22x F32y minus R22y F32x. And then finally, I get this term plus Tn equals Ig to alpha 2. Voila. Okay, that's how I do it. And I'm going to repeat that for all the bodies. Come to the second body, sum of forces in the x. I'm not going to do all this for you, but I'll show you this one. So sum of force in the x. Let's take a look at this guy. Now, there brings a little issue here, and that is, as I have the unknowns, we just talked about Newton's third law, action reaction. So I've got an F32x and F23x showing up on these two bodies. I know they're equal and opposite. I could carry them around separately. That's going to give me extra unknowns, or I can choose to keep one or the other. Let's kind of simplify and choose to keep one or the other. You can choose whatever you want, but I'm going to kind of choose the first scene. So I'm going to keep the F32x and F32y. I don't want to carry around the F23x and 23y, so I'm going to change these out. So my F23y, I'm going to say, well, that's equal to negative F32y. And my F23x, I'm going to say that's equal to negative F32x. And then I'm going to plug these in the equations, okay? I'll have to do the same for these guys, but that's what I'm going to do. So when I come to the sum of force in the x, I'm going to get a negative F3 on 2x. Now, maybe you want to do that separately. It's easy to say, well, it's a force acting on body 3, so it's a positive F2 on 3. Now I've made a negative F3 on 2. Right now, think about how you want to handle that. Just be careful with your signs. I've got the 4 on 3. I'll keep that one. So positive F4 on 3x. I don't see another force in the x, so that equals M3Ag3x. Okay, and so on. Keep just going. And then you come over here and you do the same thing. Sum of force in the x, sum of force in the y, and so on. Okay. Here you have it. Now, that's us getting equations. And we've got equations, we got unknowns. We really didn't take some time to think about equations unknowns. And I want to do that right now before we go to the next step. Let's think about equations and unknown. Let's think about what do you want to do? What do you want to think about first? Let's say unknowns on the left. Let's think about unknowns. And let's think about equations. Okay. And, for this type of problem where I'm trying to solve, I need the same number of equations and unknowns. I need the same number of equations. If I have not enough equations, I don't have enough information to solve. If I have too many equations, well, something's over-constrained. I want them to match up. So let's think about our unknowns. If I look at this problem, what do I know? Well, what am I looking for? It's a machine doing something. I probably have a motor attached, so there's some input torque. So I'm going to take my little, there's an input torque that's driving the thing. So that seems like something I need to solve for. And then I'm going to try to solve for the reactions, bearing reactions, okay? I'm going to highlight those because we replaced them. So I got these bearing reactions, I got the input torque. Then I come over here and there's a second torque on it. Now, thinking out loud, that's not from a constraint. And I've already picked my one input. So this T4 has to be some external torque that they've applied, so that's going to be a known. If somebody wants to put another torque on this, you don't put two motors on a single degree of freedom system. So I can solve for one of them, but then the other one, I'm going to have to assume that guy is known. So that one's going to have to be known, go on the right hand side. I talked about having an external P force. Again, that guy has to be known. So basically I'm going to have whatever, if it's a 1 degree of freedom system, I've got my input and then I have the bearing reactions. Let's try to count these. There's 1, 2, 3, 4 bearings, 4 times 2 reactions of each bearing. So there's 8 bearing reactions. So 4 times 2, which is 8 bearings reactions. I'll call them BG forces, BGFs, plus Tn, one input. That is 9. Okay, see how I got that? Now, in doing that counting, I was doing this replacement. I wasn't keeping F3 on 2x and F2 on 3x. I kind of replaced them. If you want to do that, you would count like, 2, 4, 6, 8, 10, 12 plus one input. So that's 13, whereas I had 9, but you then have to use Newton's third laws and you get 2 extra equations I erased that. You'd get 2 extra equations along the way. We're at the moment going to do that substitution as we're writing the equations. Okay, so that's going to give us 8 bearing forces plus 1 input or 9 unknowns. Okay, now what about equations? Where do the equations come from? They come from the free body diagrams. There are 3 for each free body diagram and 3 free body diagrams. So I get 3 equations per free body diagram times 3 free body diagrams, which is also 9. It works, okay? So you got to work that out. If you wanted to keep these bearing reactions separated, you didn't want to put the negatives, that would add 4 extra unknowns. You know, I'd get this F2 on 3x and y, and then I'd get the F3 4x and y, and I would have to add, that'd give me 4 extra unknowns, and then I could add 4 extra equations with that Newton's third law action reaction. So frankly, either one's fine. Okay, so we got the right number of equations, we got the right number of knowns. We write it in matrix form. So what I'm going to do is I'm going to write my matrix, coefficient matrix C, knowns. I'm going to list my columns right here as my knowns. So the first one, and you could do in any order. I'm just going to do the order they appear. So F12x, F12y. The next thing was F32x, F32y. You know, I had that T in. I'm going to shove that to the end. Those 2, 4, 6, 8, 9. Oh, worked out perfectly. T in. Next, I got F. That was 3 on 2. Then I had 4 on 3x, F4 on 3y. And then I'm going to get F1 on 4x, F1 on 4y. So there's 9 columns. I'll list those as my 9 unknowns. And I get 9 equations. So this is going to be you know, sum of force in the x, sum of force in the y, sum of moments for FBD2, and I get FBD3 and FBD4. So you can see the process. And I start filling them in. Let's look at the first equation, FBD2, sum of force in the x. I get a 1 times F1 on x, a 1 times F3 on 2x, and everything else is 0, right? All the other guys are 0. And then my right-hand side is this M2AG2X. About the second equation, well, I get a 1 F12y, 1 times F32y, and everything else is 0. There's none of these guys. And on the right-hand side, I get M2AG2y. Oh, and I got M2 gravity. I move it over, give me plus gravity. Okay, what about the third equation? Well, this one's got a little more stuff. What about F12x? It's got a negative R21y. What about F12y? It's got a positive R21x. What about F32x? It's got a negative R22y. What about F32y? It's got a positive R22x. It's a little tight. What about F43x? There's none. F43y, none. F14x, none. F14y, none. What about Tn? There is 1. And then everything else on the right side. So that's my IG2 alpha 2. Okay. You just keep doing that. And with having some fun, a lot of work, and some care, almost said luck, with some care, you're good to go. You got your C matrix, you got your unknown vector of F, so you got your right-hand side. You solve as F equals the inverse of C times MA, and voila, you have all your forces. Easy as that. And then you can actually set it up and run, you know, just change your inputs and keep solving this over and over if you set it up in a software. A few things to watch out for. Your C has to be invertible. Well, C has to be invertible. What's that mean? Well, right off the bat, C has to be square. It's not square. It's definitely not invertible. And the second thing, if it is square, it's got to be full rank. Every equation has to be linearly independent. As long as they're, you know, sum of moments from each, some of, you know, Newton's second law for each, Newton's third law, if you decide to do that, those are independent. Then it's just a matter of being very careful to include all the forces. You know, this is, you know, these problems just kind of keep building on your skill. They take some care, they take some thought. That's why you guys are engineers and you're good to do that. Okay. Now, I'm going to wrap this up. There's one thing I want to show you left. Here's a second example. I'm not going to go through the whole thing, same idea, but there's a new element. What's the new element? It's the slider. So let's think a little bit about this guy. We got bodies 2, 3, and 4. So I'm going to FBD2. I'm going to have an FBD3. And an FBD4. That's going to look similar. But if I look at FBD2 and like my little drawing here, it looks like this. FBD3 looks like this. So let's think about these for a minute. So I've got this pivot joint down here with ground, and then I've got the contact point there. So I'm going to need vectors R going, this is G2. So R from the center mass of 2 to 1, and R from the center of mass of 2 to 3. And this little guy, if I just assume the center mass is right at the center, everything is the center. There's vectors are all right there. Okay, let's look at what it looks like for forces. So this guy is going to be a revolute, so it's going to have forces in the X and Y. So F1 on 2X, F1 on 2Y, just like we were doing. There's going to be a mass 2 times gravity. Now, what about up here? This is a slider connection. So it's not an X and Y force. It's a transverse force, something perpendicular slider, and a moment. So I'm going to have, and I got to just choose my direction. You can choose whatever direction you want, but I'm going to choose this direction as my positive direction. So that's going to be the force of 3 on 2. You know, and I'm assuming this is my positive direction. So that's my, if this is my theta 2, then that's going to be my, this is theta 2 plus 90. That's this direction. And then there's a moment, right? I can apply a moment. So this is the moment of 3 on 2. All right. So that's how I would do the free body diagram. So that's my forces. Now I just add them up in the normal way. And what about free body diagram of 3? Well, similarly, I'm going to have the equal and opposite. So I could have I'm going to assume this is a positive direction. So that's the force of 2 on 3, right? It's the force of body 2 on 3. And this is the moment of 2 on 3. See how I did that? Now, if I don't want to carry around 2 sets, I can just replace that with a negative 3 on 2 and replace that with a negative M 3 on 2. But that's the idea. And then there's going to be the bearing reactions. This is the force of 4 on 3 in the X, and that's 4 on 3 in the Y. And then if there's any mass, M3 gravity. And this one's law works out. You sum forces in the X and Y. Okay, you got to do a little bit of work here. So for the X, it's F1 on 2X. We need F3 on 2, the X component, right? So the X component of that is going to be F3 on 2 cosine of the angle theta 2 plus 90, because I chose that as its direction, right? And for the Y, it's going to be F1 on 2Y plus F3 on 2 sine of theta 2 plus 90. Okay, not hard, but I have to expand. So it's just one unknown, but there's the X and Y. And then I'm going to have gravity minus M2G equals the right-hand side. And then moments, I'm going to have to just take the moments the normal way, and I'll have to take those as my X and Y components. And then, yep. And then over here, for the free body diagram of 3, sum of force in the X, I get the same thing. So, I could I could use the F2 on 3, but I'm going to keep the F3 on 2. So I'm going to get a negative F3 on 2X, but there is no F3 on 2, but I know its direction is cosine, or it's theta 2 plus 90. So the X part is cosine of theta 2 plus 90 plus F4 on 3X equals, on the right hand side, M3AG3X, and some force on the Y. I get okay, again, I'm going to use negative F32, the 32 terms, so negative force 3 on 2. Even though I'm looking at the forces here of 2 on 3, I'm doing the Newton's third law in my head, placing it with the negative. I need the Y, it's sine of theta 2 plus 90. Need this Y term here, 4, 3Y. I need my gravity, minus M3 gravity, and that equals M3AG3Y. And then I sum moments. And in this case, in this case, everything's passing through the middle. So I'll actually write the moments. The moment is M23. Well, no, we chose to use the 3,2. So negative M32 equals I about G3 alpha 3. Okay. If I assume that the inertia, the mass moment inertia of this guy is small, then that means this moment's going to be small. That's not an unreasonable assumption. It just depends on the size of that block. Okay. But anyhow, this is how you handle the sliders. Notice the revolute joints gave us X and Y forces. The slider gives us a force perpendicular slider and a moment. So there's still, these are lower pair contacts. There's still 2 constraints. but you got to deal with the constraints one way or the other. But voila, this is how you do it. If we were to count equations and unknowns, I would have an input. So let's look at unknowns. I'd have Tn, that's 1. And then I would have 2 at this revolute, 2 at this revolute, 2 at this revolute. So I'd have 3 revolutes times 2, which is 6. And then I'd have 1 slider times 2 because it gives me the vertical force and the moment, which is 2. I add them all up. So 6 plus 2 is 8 plus 1, that's 9. And then for my equations, I've got 3 bodies times 3 equations per body, 9. Once again, happiness, it works out great. Okay. There you go. So now all we need is just to work a bunch of problems and cement this technique, but that covers the method. Isn't that fun? Okay. Well, thanks for your attention. See you in class. Signing off.